Mark, we are doing the second part of standard work.
Yes, sir.
And we completed the part one where you talked to us about, you introduced the concept of standard work to us. You described the three elements of standard work. And now we come to the second part. And in the second part, we would be discussing about the cycle time and the standard work documentation. So at this point of time, I will stop sharing my screen and hand it over to you, sir.
Okay, I will steal the screen from you and continue on part two. Remember part one, we did talk about the introduction and the three elements of standard work. And now we're going to start part two, which is cycle time concepts and standard work documentation. So the three types of cycle time, Dr. M, that we're going to talk about today is one of mass confusion for many, many people. And so we tried to break it down to be understandable and delineate between the types of cycle time. So as you see on the screen here, there's really three types that we talk about. One, of course, is called the operator cycle time, designated by CT little o. Cycle time of the machine, CT little m. And cycle time of the process, the processing cycle time, CT little p. So the cycle time of the operator, if you go back to the first part of standard work, we talked about this whole business about a work sequence. This is the amount of time it takes an operator to perform one complete cycle in his or her work sequence. Now remember, this is for one unit in a one-piece flow environment. This is not the cycle time for an operator to complete 10 or 12 or 15 parts. This is one unit, one at a time. And that's what the work sequence should be specified as. And of course, as we discussed last time, the work sequence has to be within the context of takt time. If not, you will exceed your takt time and you will not hit your daily requirements. The machine cycle time is very simply the time a machine takes to cycle. So, if I hit the green button and it comes to a stop, that's my complete time that the machine actually operated for one part. And then the process cycle time is just taking the cycle time of the machine and adding the load and unload time of the part. So, and the reason that we do that, Dr. M, and that is really what's key to compare to takt time, is that we cannot have the load, unload, and the machine cycle time be in excess of takt time. Okay, so get into a little bit more details of these three concepts, if you will. Here's your cycle time of the operator, and as you could see, operator number one goes from if it takes 60 seconds to perform operations 1, 2, 10, and 11 back to step 1, 60 seconds is the operator cycle time. So the cycle time of operator number one is 60 seconds. Now, again, if I've got a takt time of 50 seconds, I've got myself a problem. Do I automatically take work away from the operator? Maybe. Or maybe what I do is I look to reduce 10 seconds of work out of that operator to bring him or her in context to takt time. So I wouldn't automatically just, redistribute and automatically add people. I would look at opportunities to reduce the cycle time. And by the way, the cycle time of this operator in this case includes walk time. You'll see that on the documentation a little bit later. Walk time, which we want to minimize because it's totally non-value added, is a part of the cycle time. All right. As is loading, unloading, assembling, testing, gauging, packing. I mean, all of these elements, if you will, things I just described are are things you normally find in the context of
Mm,
cycle time, operator cycle time.
mm,
Okay. Now let's understand though that if let's just say that my takt time
mm,
is 80 seconds,
mm,
and the first operator on the left and the last operator on the right, let's say, are have a cycle time of 75 seconds.
mm,
What that middle operator has, instead, takt time being 80, has 90 seconds.
mm,
Well, how often am I going to get a part off of this cell? I'm
Mm.
only going to get one every 90 seconds.
mm,
You could have one operator over takt time in terms of their cycle time
mm,
out of 15 operators.
mm,
And that one operator's cycle time would impede the drop-off rate for
mm,
that cell.
mm,
Right? You think about a Toyota car manufacturer,
mm,
a manufacturing line.
mm,
There could be 100 people on that line.
mm,
And let's say the takt time for a car is 2 minutes,
mm,
which, by the way, was something I've observed. Every 2 minutes they're producing a car. But one of those operators has 2 minutes and 15 seconds worth of work, and everybody else is within takt time.
mm,
Guess what?
mm,
I'm only going to car off
mm,
every 2 minutes and 15 seconds.
mm,
And the crazy thing about that is
mm,
it's one operator out of 100.
mm,
One operator can actually dictate the drop-off rate
mm,
for a particular assembly line in this case. And that goes for any other type of manufacturing. All right. So we want to be within the context of takt time.
mm,
Now, the machine cycle time
mm,
is basically when you hit the green button and the operation starts. Not all operations have green buttons. I understand that.
mm,
Then the machine does its thing in step 2. In this case, it looks like it's machining out a part,
mm,
and then it comes to a stop.
mm,
That's the total amount of time the machine took to cycle for one part.
mm,
Now, it gets a little bit more complicated when you got like a tombstone with 8 parts on it
mm,
and all that. And that's another discussion maybe for another day. But I will say this.
mm,
You've got to ask yourself the question, why are you machining 8 parts on a tombstone if you're going to overproduce to your takt time?
mm,
So, as a matter of fact, that one operation might put you in a bottleneck situation. So if you only need to produce one part
mm,
and you have a tombstone as a fixture,
mm,
then you only produce one part.
mm,
You don't load it up because the notion is, oh, I'm going to be more productive. I'll make 8 instead of 1. Well, first of all, you're not making 8,
mm,
because when the tooling comes in and machines one part, what are the other 7 parts doing? They're waiting. You're not making 8 at a time. Okay. And if it exceeds if it is overproduction, you don't want to make 8 at a time
mm,
to begin with. Okay. So this is what we call machine cycle time.
mm,
Right. And it's important when you're going out there and doing these time observations, Dr. M,
mm,
you actually have a clear focus on the operator first
mm,
and the machines separate. So when I'm looking at machines in this
Mhm.
particular step, that's all I'm looking at is machines.
mm,
I'm not looking at what the operator is doing. A lot of people like to combine it together and get all kinds of confused.
mm,
Right now, I only want to understand what the amount of time it takes
mm,
for the machine to cycle for
Mm.
one part.
mm,
And then last but not least, the cycle time of the processing cycle time
mm,
is a combination of what it takes for the operator to unload and load
mm,
a part,
mm,
and then of course the machine cycle itself, what we just talked about. Okay.
mm,
Now, why do we have to understand the unloading and loading time? Because the machine can't cycle when it's being unloaded, and it can't cycle when it's being unloaded.
mm,
All right. And if that is the case,
mm,
then of course you've got to take that amount of time
mm,
into consideration when figuring out whether or not your process Your cycle time of your processing cycle time is within your tech time. Now, this particular, example suggests that the machine does have to stop for you to load and unload it. All right. But sometimes, it's not the case because you've got different variations of equipment and how they're loaded, how they're unloaded, and things like that. But for practical purposes here, this is what we're talking about. Now, there's another aspect to this called tool amortization, which usually is a minor impact on this whole equation, and I'm going to ignore that right now because it's just going to confuse people. But you'll see that in the documentation a little bit later in this presentation. So here we are here with the cycle time of the process. Now, please understand though that the unload and load time is part of the cycle time of the operator that we already calculated. In addition to the cycle time of the operator, she might have walk time, gauging time, assembly time, who knows what else she's doing in her work sequence. Because the unload and the load might only be 10 or 15 seconds. And if she has a takt time of 80, let's say, she's got another, 60, 70 seconds of available time to do other things in a one-piece flow environment. Okay. This was a chart we put together to maybe visually detect this. And actually, Colleen Zapolsa actually came up with this. I give her the credit on it. I should put a little note on here that it's a courtesy of Colleen who put this into a visual format. But if you look at this operator cycle time on the left-hand bubble up here, part of that cycle time is load unload time. The cycle time of the process includes that and the cycle time of the machine, which is this other big bubble right here. Okay. So it's another way to think about it. Oh yeah, by the way, we added this amortization of tools down here too, but that's part of that as well. But that's what this is all about. So maybe that's helpful for some people on how to think about this. Okay. Now that we know the difference between, go back to this slide here, operator cycle time, machine cycle time, and the processing cycle time. Now that we know the difference, how do we use it? These are the 5 key documents that you use in the standard work analysis. And I will go as far as saying that if it's not documented, it's not a process. I think you and I did the 10 steps. Yes. 10 rules for a process. And rule number 1 was if it's not documented, you are not allowed to call it a process, right? And you look at these 5 documents, you've got your time observation sheet, your process capacity analysis, your standard work combination sheet, your standard worksheet, and your operator front loading chart, which the Japanese sometimes call Yamazuni charts. We'll go through each one. The standard work observation, this is a very confusing one for some people because, and by all due credit, it looks confusing, but what we don't want to do here is average any of these times. In this example, you see on the bottom left, I circled 26. That was the best observable time out of 1, 2, 3, 4, 5, 6, 7 observations. Well, Mark, that's not fair. Why are you using 26? Why don't you average them? Well, first of all, I never observed an average. Okay. All right. Second of all, if there are no abnormalities in that 26 seconds, that was the one best way observed and I want to set my standard to hitting that all the time. Now, may not be able to for a lot of different reasons, but as long as the operator didn't skip a step, the operator didn't, work extra hard and excessive, or already had a part built up as a subassembly that she didn't have to build in that particular one part sequence, but then later she had to, as long as it's a pure read and it really was in fact, the best time that you saw, it's not that it's unfair to use that as a standard. It's actually something to cause us to say, geez, you know what? I saw this one time at 26. How do we create the conditions so I can always hit 26? So this is where we want to go with that. And an element by element basis up there on top, you want to pick the best lowest time there. But when you add them all up, this one here came to 25 seconds. I got to add back a second. So that's how I get my element time at 7 seconds for step 4. So a little bit confusing, but I think the thing that you want to make sure of is you don't use averages. You use the observable best time that you saw, and that becomes your standard in which you want to try to hit. So again, when we do this timing, Dr. M, we let the stopwatch run. So in black, you'll see the stopwatch readings, and then what we do is just subtract out the numbers to come up with the number of seconds for every element.
Just hold on, Mark, for a minute. Just 1 minute. Yeah. Let me try this. What I hear you saying is these are achievable timings, achieved timings.
Yeah, they're not calculated from some book or some engineering stuff.
It is.
It's actually something that you observe the operator do.
Yeah, it has been achieved and therefore achievable. Am I right?
It's achieved. It actually really did happen. Yeah. Now, some of the times we let the operators actually take the times. They time each other, There's a lot of dynamics with timing too, because people might work faster because they know they're being timed. People might work slower. Okay. So you've got to have some judgment to say, look, I just want you to work at a normal work pace. That's all I want you to do. And you can usually tell what that means. So, but these are real times, Dr. M. These are not some engineering book that took some standard out of some manual and plugged it in here, right? These are actual, real, live, documented standards. Or I should say times. Yeah. Right. Okay. And again, you're gonna get the bleeding hearts to say, "Oh, Mark, geez, it's not fair to the operator. She never hit 26 but once." Okay, yeah, all right, yeah, but this is not about, this is not the benevolent society here. This is something that is we want to know why we can't hit 26 all the time. Right? Why not? And that's what we want to be able to accomplish over the course of time. It's nothing to do with being fair or being unfair to an operator. We know darn well that we took these other times that were in excess of 26. But we're curious now, and we think 26 was a normal step. We want to see how it's going to go. And that doesn't mean the operator has to work harder. We have to beat on top of the operator or anything. There could be some legitimate reasons why she was only able to produce this once. Right?
There are 2 factors in this which you have circled, which is called the adjustment times.
Yes. This is the part that's a little bit tricky, but
you take the higher end, is it, in this?
You take the best time for every line item. So if I look at get up from chair, I circle 2 seconds. Now 2 seconds shows up a number of times. Walk to board, I circle 5. That's my best time. I bring those lowest element times over, and when I add them up, because I cherry picked the lowest times. Of course, it's not going to add up to my lowest cycle of 26. In this case, it added up to 25. I have to add back a second and use some judgment here as to which element I'm going to add that 1 second back to. And I happen to pick this one here because A7 showed up quite a bit of times, and also it's the biggest element of all of them. So I indiscriminately just said, okay, that's where we're going to add back my 1 second. You know, is that scientific? Nah. There's judgment. Sorry. There's judgment involved in this. All right. But that's kind of what we do in this case, right? Because again, it would be unfair to me to use 25. That when I talk about unfair, I never observed 25 or 24 or 23 or whatever other number below 26. I never observed it. So if you do it this way, you're always going to come out when you add up those lowest elements. Usually you're going to come out with lower number than the cycle that you picked on the left, which in this case is 26. I'm more interested in the cycle than I am, because you got a lot of handoff. There's some variation here when it comes to stopwatches. You know, maybe that 1 second, 3/4 of it should have belonged in the prior step, and you know, there's got all that going on here too, right? But end of the day, you want to try to aspire to a 26-second cycle. Okay. Now, again, separating the operator from the machine is very important. When you're doing this, you're just documenting the cycle time of the operator, only focusing on the operator. Right? Now, yeah, that operator might come over and unload and load a piece of equipment, but I'm still looking at the operator. Unload is a step. Cleaning off the fixture is a step. Loading the part is a step. Closing the door to the machine and hitting cycle start is a step. All right. So all these different things I'm breaking down, but my focus is still on the operator at this point, not on the machine. Okay. I'm not timing the machine and adding machine times and cycle times together. And that's what people do, and they get really confused on this. So this whole concept of separating the operator from the machine is a very important concept. And we talked about this earlier. Okay. We can't force these things down on top of people. We got to get their buy-in. Be set with production workers themselves. I mean, Tashiono founded all this is telling us that's what we should do. How many companies out there today you think actually ask the operators to develop the standards? I know a lot of this was just based on engineering coming in, doing all the documentation, and then telling the operator, this is what you got to do. No input from the operator at all. Even if the engineers, Dr. M, were to come up with the most elegant, perfect process, the fact that they didn't bring the operators in and get their involvement, it will fail. It will fail. It matters not how perfect it is. Okay, the standard work documentation on the process capacity. So what I'm doing here is, you see I have 4 pieces of equipment, milling, drilling, tapping, and grinding. I've got my manual time, which is the load unload right here. I've got my machine cycle time of the machine. Okay, I do amortize my tool chains over here, which I won't really spend a lot of time on. It's self-evident what it is. And then I've got the total time to complete. And when I divide that time into my available time, 27,000 seconds, this is the amount of volume that I'm able to produce on each, if I were to just produce on one piece of equipment. Well, you see that our demand is 350 units. This equipment, this equipment is only capable of 303 units. So what do I do? Do I work second shift?
mm,
Do I, buy another machine,
mm,
or do I do machine Kaizen
mm,
and actually try to improve the cycle time?
mm,
The 85 seconds.
mm,
Do I do machine Kaizen? Okay,
mm, mm,
a lot of options, right?
mm,
Oh, by the way, when we talk about tool change here, I am not talking about changeover fixtures,
mm,
not changeover. This is just replacing the tool
mm,
into the tool holder. That's all
mm,
that is. If you're a machining operation, if you're
mm,
not a machining operation,
mm,
that section most likely would be blank.
mm,
All right. So this process capacity table kind of gives a picture
mm,
of do we have the equipment
mm,
that is going to in fact produce what we
mm,
need to produce. Now, you might look at this and say, well, you know what?
mm,
That we have capacity, we have capability on all of these pieces of equipment, but
mm,
we know that the tapping machine has a real output problem because the tool breaks every 20th part, and we have all kinds of issues with downtime, and so let's build that into the stand. No, again, that's where you have to go in, and this is when the machine works perfectly. That's what we want to see.
mm,
But if you're not able to hold to that standard, then of course you got to do Kaizen. You got to figure out what's going on. Okay. So that's how we look at this. Now, I might also want to use this chart to say, hey, you know what, guys? Our
mm,
takt time is going to get faster, which means our volume's going up. I
mm,
now have to do 400 units a day, not 350.
mm,
Okay. All of a sudden, that brings milling operation one into consideration to say, guess what?
mm,
When our volume eventually hits 400 a day, we
mm,
don't have capability on milling. So I could use this tool also as a sort of pro forma looking forward type
mm,
of thing, saying when our volume does hit that 400
mm,
greater, I'm not going to be able to produce on milling the way I am today. Right now, milling is not an issue.
mm,
My volume is 350, and my processing capacity is 385.
mm,
Not an issue, right?
mm,
Now, another way to think about this instead of quantity is actually look at that column where it says total time to complete and compare that against your takt time.
mm,
So in this example, my takt time 77 seconds.
mm,
And if you look at operation number 4, again, you could see it's violating that takt time at 89. At 89.
mm,
Okay. So that's process capacity. Now I take both of those. I take the time observation sheet, which depicted the operator cycle time, and I take the processing capacity, which is the machine time, and I combine them on a combination sheet. And that's what this is.
mm,
So you can see here all the steps involved: pick up raw material, unload, load, start mill, unload, load, start drill, gauge part, unload, load, right? These are the different steps. And if you took a look at the manual steps, 52 seconds in total, and the walk steps, 18, that gives me a total time of 70 seconds. When I graph it out, you could see where we are, right? And that squiggly line that comes up to the top stops at 70 by 70 seconds. And this is called wait time. I physically have wait time to takt time. Okay. So you can see we split out walk time separately because it's a waste. The dotted lines are the actually automated equipment, the machine cycle time, and the dark bars are the operator cycle time. So I'm comparing this now visibly, and I'm drawing my takt time. Oh, guess what? In red. Here we go. Here's my 77 seconds. All right. Now, if I look at this and say, well, geez, where's my opportunity to do Kaizen? Well, it looks to me like assembling the brackets is taking a lion's share of the time. So how can I make some improvements there to make that a little bit more robust, less time, more efficient? And so that might be where I go at this point. Okay. Gauging part. A lot of times you're going to see, oh, we gauge 1 out of 10.
Mm,
So we're going to put 1/10 the time in there. Again, I go back to the notion that says you got to assure your quality before you pass it on. So like I said in one of my other webinars with you or vodcasts, Mr. Iwata couldn't understand why we didn't check the other 9. Oh, because it's SPC. Yeah, but you know, you then are not assuring the quality of that part. You're violating a principle. And finally, what convinced everybody was when he said to us, would you fly an airline that only checks 1 out of 10 airplanes? And we said, no. Okay, well, you got to take the attitude with your quality too, right? So even though checking and inspection are their own beast themselves because they're not always reliable or repeatable, but what you want to do is build quality into the process so you don't have to do inspection. It's always a good cocktail party discussion if you're with a bunch of lean gurus. Hey, is inspection value added or not value added? You won't believe the arguments that will ensue. So that's the combination sheet. 1 per operator, by the way. 1 per operator. So this happens to be the work sequence, Dr. M, from 1 to 7 for this particular operator. And then you can see there's a 3-second walk time. This operator walks back to the first step again and repeats. Now, technically, they're supposed to stand there for 7 seconds. If they're in the middle of the process, they're going to have to, because if the other operator is loaded to 77, they'll have no parts to run. So, or won't have a part, I should say. So technically, they're supposed to stand there. And why is that? They're supposed to stand there because we want to visibly see that there's waste in the process. We don't want them doing all kinds of extracurricular things that aren't dictated by their work sequence. That's another visual cue. And there's a lot of training that has to go on to that, because most people have been trained all their life to just look busy. And it should not be a reflection on the operator, it's a reflection on the process. Now, I may say, hey, you know what, this is the last step in the process, and I'm packing over unfinished goods. Maybe I can bring the packing into the cell and pack it right there. Why not? And I could fill up that available time with additional cycle time for the operator to bring me in closer to tack time. All kinds of things you can do. This is the standard work sheet that shows you the flow of the operator in context of the cell. So you can see how we have the cell layout, and you can see that this particular operator goes from 1 to 7, and then walks back to 1, which is a work split. Okay. Down below, you got, down below, you got standard work in process dictated. There's 4 pieces. Tack time on here. You got your cycle time. Okay, you got the part number up here. You got your quality checks laid out. So right between drilling and tapping, I'm going to do a quality check. And that's the layout. This goes back to the notion I think I mentioned earlier, Dr. M, where Nikal could not understand how Americans would say they know something, but never done it, or couldn't do it, couldn't demonstrate it. So Nikal came in one day to my factory, and I said, Nikal-san, we need to work on SMED and TPM this week. Deluzio-san, we need to work on standard work. Nikal-san, I already know how to do standard work. Come on. I could do operator loading charts, combination sheets. I can take time observations without a partner. I'm that good. I could. He says, come with me. So he takes me over to the shop. He looks at one of my lines, a brake housing assembly line and machining line. He looked at the standard worksheet, which was this one. And he saw that I called my standard work call for 5 operators. And he said to me, how many operators Deluzio-san are in cell? I looked and I said, well, there's 8. Deluzio-san. Oh, actually, what I said was, there are 8 operators, but you must understand, and he cut me off. Deluzio-san, you do not know standard work. Okay.
mm,
So if you're ever working with anybody like Nikau,
mm,
be careful telling them that you know how to do something.
mm,
You cannot demonstrate
mm,
that you did it. You know, I
mm,
use weight as an example. If you're 500 pounds,
mm,
you can't tell me you know how to lose weight. Oh, yeah, I do. I can tell you how to lose. Do you really know? Okay. Do you have the discipline to really do it? Do you really know? Can I really sit here and tell you, Dr. M, what all the proper techniques are to hit a golf ball? Yeah, I can. I
mm,
read all the books,
mm,
but I can't do it.
mm,
My ball goes into the desert all the time.
mm,
So how can I sit there and say I really know how to golf?
mm,
How can I say that?
mm,
That's a mindset issue. You and I talked about mindset
mm,
um, at one of the other podcasts. That's a mindset issue. So anyway, so again, I was young and I thought, I knew I had this all stuff laid out and knew how to do this. But until you have to pick up the golf club and swing the club and see where the ball goes,
mm,
you can't say you really know this stuff.
mm,
Okay, the front loading chart. Now, this is an interesting one because as I go through and I take all the times
mm,
on my initial cell,
mm,
and I've got all these operators here, you can see all their varying cycle times, which are all over the place
mm,
as it relates to the tack time of 60
Mm.
seconds.
mm,
But I go back and I do some Kaizen and I redistribute this work.
mm,
And you can see everybody now is within the context of tack time.
mm,
And oh yeah, by the way, the base assembly guys went away because I must have incorporated that into the sequence. So in other words, I went from 11 people to 9 people
mm,
in the after section down below.
mm,
And they're all within concert attack time. Just Nakao told us sometimes load them a little bit over tack time because learning curve are going to get them down below tack time.
mm,
So that was his theory. So so here we go. So this is the operator cycle time by operator.
mm,
And let's say I didn't do any Kaizen per se.
mm,
I just redistributed the work,
mm,
but everybody front loaded to tack time. Now why do I want to do front loading?
mm,
All right. If these are my initial times,
mm,
and I balance everybody.
mm,
Bob Pentland used to kill people that would say, I'm going to balance my workload.
mm,
Well, now I've got everybody below tack time and I got all that waste. I'm going to overproduce in this case.
mm,
All right. Unless I stop the cell at 4:00 instead of 5.
mm,
So I don't want to balance.
mm,
What I want to do is I want to front load. So I want to take all that waiting time that you see here
mm,
and put it into one operator called the lease operator.
mm,
Well, geez, Mark, why did you want to do that?
mm,
Because I want to see it visibly. And the point of the matter is that when I end up taking more cycle time out of this front loaded concept,
mm,
I don't want to end up with a situation like this up here again in this initial time situation.
mm,
So I'm going to redistribute and recalibrate everybody back to tack time. And that will just essentially knock down the amount of time for the last operator number E. Okay. So now you say, well, geez, that's not fair to the operator, or the other operator's got more work than the least operator. This again is where rotating comes in.
mm,
Everybody learns everybody else's job.
mm,
And again, you really do want that last operator, that least operator, to stand there for half the cycle time so we can see the waste.
mm,
But like I said earlier, maybe I do bring in some other work for that particular operation that's being done somewhere else.
mm,
Okay. But I don't really get to have headcount reductions. And by the way, that doesn't mean laying people off. Headcount reductions to become more productive in a cell unless I front load. Because if I do the balanced approach here, I'm always going to have 5 operators.
Mm.
All right. So that's why we want to do the front loading least operator. And by the way, least operator sounds demeaning. It's not what we're mean. It's the least cycle time operator. I should probably change that, but you know, and the operator's got to understand that this is not a reflection on you. Okay? It's a reflection on the process. Okay. So that's how we use these operator load charts. But balancing is a big controversy out there today, and that's not how we were taught. Operating procedures, I told you, are different. Standard operating procedures are different than standard work documentation. Okay. And again, you can't use lean and Kaizen to reduce heads and send people off the door packing. The last time you're going to get any input from any workforce employee at all going forward. Boy, geez, last time I had 12 people in my cell and we did a Kaizen, ended up with 8, and 4 of them lost their jobs. Now you're coming to me and saying, Mark, I want your ideas on your cell. No, you're not going to get my ideas. Okay. It's a train wreck if you try to do lean with a no layoff policy, without a no layoff policy. Okay. And there are some notable CEOs out there today that just laid scores of people off, and they're wondering why they're not making progress. Because you're not getting the engagement of your workforce. That's the problem. You could see some of the results of what happened at Jakebreak. Okay. Like I said, one of the first things we did was implement standard work and one-piece flow, cell design. And again, those people out there that say, well, you know, you got to get rid of all your problems first, then standardize, is just categorically wrong. Absolutely wrong. Okay, I think that's the end of that. Dr. M, just one thing on the documentation, there's a lot more detailed instruction that we give people when we do a standard work Kaizen. Okay. I didn't think it was appropriate to bring that in here, but it's not too unlike like anything that you do that's a lot more detailed to behind the scenes. But hopefully these 2 sections that we did gave people a good framework of what is standard work, what it's not, right? What it's not, and what are the elements of it, what are the steps involved in it, and all this stuff. So to me, the best way to learn this, once you go through some brief training like this, is go out and do it. So many people put it off. So many people say, well, you know, we've got to get our act together. We have to do this. We have to do that. You put it off. You put it off, and you put it off, and you're never going to make improvements. It's kind of like saying, I'm going to, you know, how do you start a workout program at a gym? You just go and do it. You just go. You got to get there first and start this. Yeah, albeit it will be imperfect. But so what? If you pontificate about this, you'll be pontificating forever and take a real pedantic approach to standard work, and nothing will get better. Nothing will get done. Let's go out and do it. That's the real key.
Just one thing that I wanted to ask you, and I'm sure you know, where does these documents go?
Oh, you know, that's a slide that we don't have in here right now, but if I were to go back and tell you, I like to see that the standard worksheet and the operator combination sheet go at where the work sequence is by operator. I like to see it right where the operator is. Then I like to see the time observation charts do not have to go anywhere. You can just keep those filed, but they're there for reference. But the standard the operator loading chart
Mm,
and the process capacity chart, which are the other two documents,
mm,
should be posted at the mouth of the cell
mm,
on your production control board or whatever you use there, right? That way I can walk up to that like Nikau did to me and say, hey, how many people are supposed to be in this cell? I said 5. How many are in there? 8. Okay. Abnormality, you know, okay. That's why. Also, the work instructions will go up with the standard work documentation as far as the standard work combination sheet and the standard worksheet. Okay. That type of thing. So yeah, so we would like to see them posted is the best thing. And it's also a way for you to be able to tell if an operator is going outside of their work sequence.
mm.
It's another thing to think about. So, but anyway, that's what we would do with
That's
them.
good. Yeah. Every time we improve a standard, because either the demand has gone up, there's a lot of demand, and therefore you need to revisit the standard that you have in place. And you do it the way you have explained it. So these have to be documented with version 1, version 2, version 3. And it is not where I see in the Gamba is that the versions are not mentioned. The dates are not updated. And these are the flaws I'm sure you and I mean all of us who have been in Gamba and we notice all that. I just want to reinforce that that is an important part of standard.
We had a rule of thumb, and I'm not suggesting to you that this is the right rule of thumb, but our rule of thumb was we wanted to see your standard work updated at least once every month.
Mm.
Now, what would cause you to update your standard work?
Mm.
2 things.
Mm.
One, if your tech time changes because your demand changes,
Mm.
that has to all be recalibrated in terms of how you assign work and how many operators and all that good stuff, right?
Mm.
2 could be you did Kaizen
Mm.
and you took cycle time out, which again needs to be reflected in new standard work. So those are the 2 major reasons why you would end up changing your standard work documentation. Okay, and it's good evidence to say that Kaizen really is still going on, right? But if you see stagnant standard, I had one client, they knew I was coming in to see their best plant in the company. And they had standard work posted just like we talked about. But they put a sticker over the date and put the new date on it. It's like, I know I look stupid, but you know, it was like, no, guys, no. It was a year old. And it wasn't appropriate because when I actually challenged them and looked at the process steps, they were different. As a matter of fact, it wasn't even for the same model. So the model A was what was documented, and they were actually doing model B, which was similar but different. So the steps weren't even the same. It was just all it was, again, this is that's when you get to this whole dog and pony show with your leadership. And look at me, how great I am. I'm doing standard work. I got all the documentation up, you know, and you know, this is the same plant, by the way, that when I did their morning walkarounds on their Gemba, they had a production goal of, let's say, 500 units, and they hit 650, and they marked it green, and they marked it that it was a good situation, a favorable green situation, rather than a red negative situation. Why'd you guys mark that green? Well, because we beat our plan. But you overproduced. No, we just beat our plan. Wait a minute. If you said you needed to make 500 today, isn't that based on reality that you have demand for 500? Yeah. So why'd you make 650? I will eventually sell it. Oh, really? You turn inventory 2.5 times. Which is almost like 6 months worth of inventory. I said, why don't you go sell that stuff? Okay. This is the stuff you walk into with these guys, and they want to rationalize everything that they're doing. That's not in context with the principles and philosophies. So Hey, there may be times where you have to violate a principle, but you better darn well do two things. A, mark it visibly so everybody knows, and B, have a plan as to how you're going to get out of it. You know, I mean, from that respect, I'm a realist. I know things happen, right? However, you can't just let that become your new normal, your new standard. You can't let that become your new standard. That makes sense. I mean, that's, sounds logical, but I've seen it happen again where there's, it's the way it is, So, all right. Do you have any more questions or?
No, I was just thinking that maybe when you're relatively free, and these two I publish in a gap of 2 days, so that the internet or the LinkedIn cycle takes place, etc. And people absorb the part 1, and then I put the part 2. Otherwise, many of them will see the part 2 first and then the part 1. So I'll do that. And maybe once that is done, we call a small group, and I would like to have an interactive session with you with 3 or 4 people. And they can throw the questions around so that, we again keep digging into this. I mean, like what you talked in the first thing of repeatability, stabilizing, whatever you want to call it. So it gets impregnated that, look, this is what I mean. So from both of us, we spread it around, but I'll try to get a couple of people around who can ask more questions and be interactive, and I will publish that too. So that becomes my improvement plan on my podcast.
Okay.
Thank you very much. Good. I'm sure you're going to be there for me, Mentor. Thank you very much.
Oh, no. Look forward to the other ones we're going to do. Take care.